All right, so can I start with a quick show of hands? How many of you have used Cassandra in like production or testing environment, just out of curiosity? Okay, so decent number. I assume the rest of you are just kind of evaluating this and kind of understanding like how to grow it, which is hopefully what I'm going to focus on for you. Basically, I've worked at this company called Signal, formerly it was called Brighteg. I've been there for about 4 years. During, say, 3.5 of that, I've been working with Cassandra in some shape or form. So I'm trying to share basically the lessons we learned and kind of like why we chose it and why we adopted this technology to solve some of our really hard problems. So what Signal actually does, we're in the ad tech space. We help make it easy for marketers to configure stuff and interact with their audience in hopefully the same way. We kind of pull out some of the necessary of the development cycle to actually get these marketing technologies implemented. And we've since expanded from web-based stuff to kind of cross-channels and mobile and other places. So we kind of have 3 main Cassandra use cases, and I'm really just going to focus on one of them for this talk because I think it's the more interesting out of all of them. But I'll run you through just a high-level summary of what we're doing. So the first case is this kind of matching service, and it's a kind of a well-known thing in the ad tech space. Basically, it's a way to like associate identifiers between different companies or between different services. We use it to provide what we call a unified customer view. So when our clients interact with their customers, they can see a bigger picture. A lot of this is geared towards measurement and activation. So measurement is purely like analytics, like how many people do I have, that kind of stuff, slicing and dicing the data. Activation is more about, I want to take action on this. Now that I know who they are, I want to like, send them promotions or do whatever it is. The second use case is actually quite along with Sandwich for Cassandra. It's, I want to store some sort of time series data, usually about metrics or about values of things. So we've played around with a couple different backends to use Cassandra, Kairos and Sinai. They're both open source projects, you can check them out. We've had some success with them, also some pains with them. I won't go fully into the details of those, but basically it's something we have played around with and we are actually using in production. And then the last case is a newer case. It's kind of like an audit log of events that come in and we just want to track what's happening. It's not very interesting for data modeling, so I'm going to toss into that too. So really focusing on our first use case. I apologize, the colors are a little bit bad on display, but basically we have a lot of different sources where our clients can send data from, so there's CRM systems, websites, mobile apps, etc. Those all get channeled into our system. And really where we use Cassandra is in this middle, the blue box. It's all around our matching service and that kind of functionality, and then that ultimately gets used to kind of funnel data out in real time and let them take action on it. So just like a little bit of background timeline. So I said I've been working with Cassandra for about 3 years. So we started in summer of 2011. Basically, we evaluated Cassandra. Before we chose it, we compared it to Couch, Mongo, and React to kind of get an idea of what NoSQL solutions were out there. We had a kind of flexible data model, but we knew we definitely wanted data to replicate between regions and a few other constraints about the consistency of it. So ultimately we decided on Cassandra, and when we finally got into production, 1.0 had just been released. So we deployed it to 2 AWS regions with 8 nodes. It wasn't that impressive a deployment, but we felt good because we actually had it replicating across the regions. And our very first schema was really simple. It was just one data table. This is back when there wasn't CQL, it was all thrift-based. So instead of one column family, there's some other options on here for thrift style, but that was basically it. So what did it actually look like? What we were trying to model was effectively a sparse matrix, and it worked really well with how SS tables store data. So we had a row key, which was some sort of internal identifier, and then that mapped to one or more columns of some data that was sparse. So there may be data there for some rows, not for others. And this worked really well for our first trial of this. This is what we went to production with. So from there, we had learned some stuff. We had acquired some use cases for how we wanted to interact with the data. And we also started really buying into the Cassandra ecosystem, if you will, and having to deal with upgrades and think about how we want to really model and query our data. So part of that was we were looking at other tools to help us manage our Cassandra installs. One of those is Preempt by Netflix. They basically help you organize your security group rules and do backups and some other stuff. Since we run all our services in AWS, they're Linux-based, this was a great way to kind of manage the security rules for us. Because basically, no one wants to set all those up. One of the other things we learned is, or tried to do is we wanted to not have just a single identifier per column in our match table. We actually wanted, in our sparse matrix, we really wanted like kind of a map or a set of multiple things there. And there's usually like a primary identifier, but there's often sometimes secondary ones or other pieces of metadata that we want to store, or actually our clients want us to store for them as part of this. So we kind of took a swing at this. There's actually a thing called Composite Types, which is probably what we should have really used. We didn't have enough time to fully prove out that it worked the way we wanted to, so we kind of did this hack solution. And that worked for a while and got us to the point where at least we could meet this use case and kind of keep evolving our Cassandra. And the other thing we did is we added our first index tables. So like they mentioned earlier today, Cassandra isn't relational. You can't do a join across tables. And there is a secondary index, but it's not recommended to use it. So what we basically did is we built our own index tables to map to how we wanted to query the data out of the main table. So for each thing that was a potential identifier in the main table, we would enter a row into the index table so that we could find out what our internal ID was, and then from there be able to discover everything else. And this once again is kind of evolving use case of how we wanted to access and what we want to do. This was just the next phase of that evolution. So the next thing we had to focus on is we kind of hit one of those hockey stick inflection points where we had enough usage and we knew more about it. We really need to look at ramping this up, and we want to make sure that as we did that, we could test what we were changing and test new versions compared to the old version. So we built a load driving framework. You can use something like JMeter with a plugin, or we had some other stuff that did a little bit more fancy controls between like read and writes to give us an idea of what it would look like with a comparable amount of generated traffic. Or so compared to our real-time traffic, we kind of generate a roughly equivalent proportion with the load driving framework, so we can actually compare, does the newest 1.2x line, is that equivalent to like the 1.1 line that we were on? As part of this, we also worked on redesigning our schema. We made some adjustments to it to support some of our new query patterns. And the final thing we did this year is we upgraded to virtual nodes. So they didn't really touch on it too much today. Before virtual nodes, every time you added a new node to the ring, you would have to kind of reallocate the token space on your own and kind of slide around what data you're responsible for. Virtual nodes let you not have to do that. Previously, it was very easy to scale a range by doubling its size. It wasn't as easy to scale by other amounts. Doubling made it easy because you split each token range in half. Virtual nodes kind of takes care of a lot of that for you. So it was a big one for us because you had to scale with actual traffic volume, not based on just doubling the number of servers. So as part of this, when we switched to the 1.2 line, we had to use CQL for the first time. So we created basically a new Keyspace, and it's done a little bit differently now. So when you create the Keyspace, you can set up how you want to replicate it, where you want it to. So the initial strategy we went with is we wanted 2 copies in each of the 4 regions we were going to be in. These copies are, you can control how you write it out. You can say, I want the copies to be everywhere before my save is done, or I want it to be at least in my region and then replicate everywhere else via gossip. So it gives you some flexibility, but we said we knew we wanted at least some copies of data everywhere. One, it's for redundancy. It also gives us the ability that if we want to, at a higher level on application stack, take a region offline temporarily, the data is still available somewhere else, or if we need to shift traffic, it's still available somewhere else. So our data table is now a little more interesting to talk about. So what the data table really is its own, our own signal internal identifier. Identifier is basically who this data is for, a map of the IDs or the identifiers that we have available, and then a map of like the other metadata we have available. And along with an internal one. So internal was just for us, let us do things like effectively replicate like a create time, modify time, etc. It also let us store other information that was useful to our system, either querying hints or one of the big things that's popular in ad tech space is privacy. So we can store privacy information here. If someone's opted out of it, we could store it in this place. So what this would actually look like. Oh, sorry, one more thing I forgot to mention. So the other thing that we changed to is our primary key went from just our own internal identifier to our own internal identifier clustered with the identifier for who this is for. This let us still have data that's basically fat rows, but we can cluster so when it gets returned by CQL, it looks more like a relational store. So what these tables would actually look like when we do the query. This would be an example, so we might have still the same sparse matrix type of field, but it's now in the SQL more relational format. So we would have, this one signal ID of A111, and it can have, as many rows associated with this as are needed based on our client's configuration or whatever setup. And then we have IDs for each one and potentially data for each one. And if there's nothing there, that's fine too. That's handled as well. So are there any questions so far about this? So also we redid the index table. So the index table is now set up where we have the identifier as the primary key along with a partition, and then there's a ID name and an ID value. This is building the same reverse index. So whoever this information is for, what the name of their identifier is, what the value of it is, and then what our internal ID is. So it's the composite primary key is identifier and partition, and then the whole key is also clustered by the name and the value of the ID. So how we actually figure out what the partition is, this is purely something that's done at the application level. We just compute, it's basically a hash mod, the number of partitions we want of these values. We've actually used this in a couple other places now too. It's a very effective way to kind of partition our data up. So if we want to run a query, some clients may have a lot more data in here than others. The very large ones, the queries will always time out because you can query it all in one go. Or you can get clever and try to query just part of the token range at a time. This allowed us to query by a partition at a time, so it's kind of an artificial constraint, just like saying limit, n, but this is a little bit easier way for us to query by applications. So another interesting thing, so when we move to virtual nodes, there is theoretically a way to go from a ring with non-virtual nodes to virtual nodes. I've never actually heard of anyone making it work. It's called a shuffle. We were told at DataStax not to use that because they have not heard of anyone making it work either. So what we did is we took our old ring, left it where it was, and made a new ring with all the new nodes set up in it, with a new schema, and virtual nodes enabled, like side by side. And then we changed our data access service so that we could read from both and then only write to the new one. So that allowed us to start migrating over organic traffic from the old ring to the new ring. And then alongside that, we had a migration script that ran through the old ring and forced the writes that happened to the new ring. So overall, that whole migration took the course of about a week or so. We didn't push how fast we could go. We don't kind of want to go to the slow scale so that we could maintain a roughly equivalent performance level. We did have some extra latency due to potentially two reads that would have to happen. But overall, we were able to keep the system up and do the migration kind of on the fly without having to make anyone the wiser about what we did with it. So we might actually be going through a similar process again with some of the changes we're looking at in the near future to apply those, because you can do basic alter table commands with SQL. Some of the more advanced ones, it's almost harder to try to alter them and make sure your data is consistent than it is to just kind of copy and rebuild. So this is a pattern that we may continue to use going forward. So really 2014 was mostly about scaling and focusing on performance. It's also when we first started looking at Kairos DB as well. So one of the things prior to this I didn't really mention, I said we were running on Amazon. I didn't really say what we were running on. We were running on these kind of crappy M2 X larges, and then we upgraded to these M2 2X larges. They were fine, we could RAID the disks, but they weren't that fast. We had a lot of spikiness with our latency. It was kind of all over the board. What we found out through both seeing some reports published by Netflix and then our own bit of experimentation, that if we put the same thing on one of the I2 instances, which is basically an SSD backed instance instead, it made a huge impact in our latency, kind of really leveled it out. To the point, sorry to turn back and can't see, but basically the blue line here is our write latency, and the green line is the count of how many we've done. So you can see it's kind of a cyclic pattern. This is over the course of 4 or so days. We basically applied the SSDs that were the first markers, and that smoothed out a lot of our kind of funkiness from this. Sorry, this is 4 weeks, not 4 days, by the way. It smoothed out a lot of our kind of spikiness in the latency. And then once we actually did the upgrade to the 1.2.16, which was the latest patch at the time, and it had a few other fixes for, I can't remember the specific patches, but something to do with the latency and how something else is calculated, it really kind of really smoothed out our overall latency. So we're at a nice low steady hum, regardless of what the actual volume is. So we were probably over provisioned previously to handle the volume, but we didn't know that because of the basically bad performance of our hardware and potentially older versions of the code itself. So read saw a very similar change. Same thing. We had a lot of spikiness in our read latency. It's also same thing. Blue line is latency and green line is the count. And then as we did the upgrades to SSDs and then did the further upgrade to the 1.2.16 line, it kind of smoothed that out and got a nice slow steady hum, to the point where we stopped trying to make more performance tweaks that we had queued up in case this didn't work. We're now have either done some of those or looking at still doing them because as our volumes increase, we hit new bottlenecks. But just because kind of like staying up on the hardware and staying up on the versions can definitely make a huge difference. So this year we've done a few new things that are, I guess, interesting or different than what we've done previously. We've added a new region without completely rebuilding the ring. We added Sydney to our cluster of 4 regions. We also rolled out our new audit log use case. We have some planned schema redesign stuff, which is where I said we might do the whole migration process again. And then kind of tying in actually to the previous talk you guys saw here in this room, we started looking at Spark for kind of batch jobs and reporting and potentially getting some metrics about the data we stored in Cassandra. So most of this is driven by client demands. They want to know how many things we have stored for them. So first, let's go with the new region. So we currently have 4 regions that are up and running: Tokyo, Europe, East and West in the US. Those are all synced up in the normal Cassandra ring. And we decided to add Sydney to the mix as well. So Sydney's a little bit different. It's going to be used as a read-only copy, where we're going to run the batch jobs and like reporting stuff against this. So it doesn't have the heavy write throughput coming through it. So if you want to apply caching or do other strategies, it'll be different in Sydney versus like one of the other 4 regions. So the other 4 regions would have be geared towards more real-time random access patterns, versus Sydney is going to be much more like a table scan type operation to compute its data. So one of the other big topics that we needed to focus on this year, I said, is like latency. So we have a lot of spikiness from the application level, because in our applications we may be doing more than one read or write to service a request, because there may be, based on the set of parameters that come in or based on what we want to do, we might have to do several lookups to get what we ultimately want. So this is broken into the blue line is the mean, green is the 75th percentile, purple is the 95th, and red is the 99th. So you can kind of see that on average we have a pretty steady hum of latency, but we definitely have a lot of spikes that we're trying to figure out how we can iron those out to give the best possible experience to our customers. So that's one of our challenges. This is where maybe we look at a more aggressive caching layer. We're already using stuff in Cassandra. We possibly will do some stuff at the application layer or other places to try to influence that and bring that kind of down. And the same thing for the read side too. Write side, we don't care as much about the caching, obviously, but for the read side, that's where it makes more of a difference. And we actually care about keeping this latency as low and steady as possible. We have some internal ballparks we would like to hit, like 10 milliseconds would be awesome. Maybe it won't happen this year, but let's just keep chipping away at this and get it so our 95th percentile is much lower. So back to the metrics and reporting. We have been doing this for a while. It's been a customer client request. We've been running this as a bunch of ad hoc Python scripts. So if anyone who's ever maintained an ad hoc collection of things, it can get kind of gnarly and hard to work with, and it's not a very consistent feel for our clients sometimes. So what we're trying to do is, or what we're looking at, I guess, is we're considering either adding specific reporting tables, where those will be written to at the same time. So this goes back to the data duplication. We'll write it to our real online kind of tables and our reporting tables at the same time. These will be centered mostly about set membership and overlap, and kind of giving that kind of counts. Alternatively, we may look at using something like Spark to help pull out numbers and to kind of compute those numbers and crunch them periodically and kind of give us an idea of what's going on. So we haven't decided on one of those yet. We're actually probably going to do some spikes in internal discovery before we commit to one or the other, but those are the things we've been considering. And so some actual stats about our ring. We've grown a lot, so normally we start with 8 nodes. We're now to 140. So we've definitely gone through a lot of the growing pains and curves of getting from a small, effectively, test or kind of prod system, or like beta system up to like a full-size system that's actually used in production. Now we have an estimated 15 billion rows in our data table, so it's grown quite a bit from our initial use case where we were like, oh, we're going to have hundreds of thousands, maybe or a million, maybe if we're lucky. So we're quite a bit past that. We also have a very large index table to support all the ways that we want to look at our data. And then overall, this is about 30 plus terabytes on disk across 140 nodes. So the real reason why we partially chose Cassandra, not just because of the things it can do for us, but it's also the failure cases, because I mean, stuff happens all the time. There's nothing you can do about it. So we survived a ton of things that would either possibly cripple other databases or make it very hard to deal with operationally to guarantee uptime. So we dealt with Amazon swallowing nodes when they did the massive reboots to apply security fixes, disk failures, corrupt SS tables, and just normal networking glitches between regions or between nodes in the same region. So, like I said, there's some advice. One is don't skip on your hardware. SSDs work really, really well with Cassandra. You don't want to use like a RAID, you don't want to use like ES, actually just use the disk on the machine. You want to stay current with the releases, maybe not too current because there's sometimes bugs, but like, roughly up to date. And then one of the things that bit us for a while was keeping up on repairs. We had started to fall behind because our data set was so large. And then fortunately they introduced a way to slice up repairs into smaller ranges. So we were able to use that to like minimize the amount of time we have to run on each repair to actually be able to keep up with our current volume and load of data. And then, like I said before, testing is really, really important for this. So we spent a fair amount of time figuring out how to build a testing framework to drive loads to this, to make sure that as we make changes, they don't negatively impact performance. They can, we can try, two different things like an A/B. We can simulate different levels of load, different amounts of read versus write. So that's just really important to maintain a stable system. And possibly the best thing, if you're thinking about how to model your data, is really figure out like what questions you want to ask, and then how you want to store the data to answer those questions. So we've spent a lot of time kind of whiteboarding, figuring out like what does our data look like, and kind of going through iterations of it. So like I said, we have some stuff queued up that we know we want to change based on new usage patterns and new questions we want to answer. And so it's really going to make sure you have the data mapped or available in the best way. Even if it's duplicated, it makes the most use out of Cassandra. And are there any questions?